Let's look at example 12.5, flywheel. Here we have a flywheel. So it's like a disc, okay? A motor exerts a constant force of 120 newtons, tangential to the rim of a 20 kilogram cylindrical flywheel of radius half a meter. The flywheel is free to rotate about an axis through its center, okay? Let's see. If the flywheel is initially at rest and the motor is turned on for 2 seconds, how much work does the motor do on the flywheel? How much work does the motor do on the flywheel? Okay, so a motor is exerting this tangential force on the flywheel. Okay, and so we know what we've been hearing so far is that if we have this tangential force, or if we have a force with a tangential component, anytime there's this tangential component, let's see here, we have an external torque, because the external torque is F, it is this F, this perpendicular component times R, okay, or it's the perpendicular distance times F. Okay, but the point is that whenever you have this external torque, you have a change in your momentum, your angular momentum. In the same way that when you had an external force, you had a change in your momentum, delta P, in a linear way. Remember, that was linear. Okay, so keep that in mind as we look at this. But the question is, how much work does the motor do on the flywheel? Okay, so we know, let's consider, actually the only energy change is kinetic energy. So remember this guy, W is equal to delta E. So the work done changes the energy of the system. Okay? But now the only energy change that we're looking at here is kinetic energy. So this would be K final minus K initial. Remember, delta K is K final minus K initial. So the only energy change we're considering is this change in kinetic energy. The next thing is we know that the initial kinetic energy is 0 because omega initial is 0 because it starts from rest. Okay? So this force is doing work. This is what we're trying to find. Right? This force is doing work. And the work is equal to this final kinetic energy. So what is this final kinetic energy? We know that kinetic energy is given by half I omega final squared. Remember, in a linear sense, kinetic energy is half mv squared. Okay, so what is this guy? This is your rotational inertia. And for the most part, all you need to go to is, if I'm not mistaken, it's table, is it 11.3 or 12.3? Hold on. Let's see here. Table 11.3. Go and check out table 11.3, and you'll see that for a disk, your rotational inertia about the center, okay, is half mr squared. Okay, so we've got this guy, but we're looking now for this final rotational velocity after 2 seconds. So how are we going to find this? Well, this is where we come to this idea of change in momentum. So because there's an external torque, we have a change in angular momentum. So we know that, first of all, angular momentum is equal to I omega. Okay? Remember, the linear equivalent is P is mv. So here's your rotational inertia, there's your rotational velocity, there's your inertia, and there's your velocity. Okay, so you want to look at, whenever you get confused, just remember what is the one that you know in terms of linear motion, and then you can figure out the rotational equivalent. Okay, so delta L, which is an impulse, angular impulse, is then equal to, what is going to change the momentum? It is the sum of all your external impulses times time, delta t. Okay? Remember, linear impulse, J, was equal to the sum of all your external forces, delta t. So this is the rotational equivalent. But we also know that delta L, theta, is equal to I delta omega. I delta omega. Is that making sense? My change in momentum, angular momentum, is I times change in rotational velocity. The same way that delta P is M delta V. Okay? So now we've got these guys, and we can see our omega final is hidden inside there. So we've got the sum of tau external, delta t, is the inertia, and this will be omega final minus omega initial. And we know omega initial is 0. So if we solve for omega final, we're going to get tau external delta t over the inertia, rotational inertia. Okay, and now I'm not going to do the rest. You can do the rest. But this is the idea of, I just wanted you to see the idea. The first big idea is this. Work is delta E, and we saw that the only energy change that we're considering is delta K. Then what is that? That is equal to half I omega squared. And how do we find this guy? It is by this over here, these relationships over here. Okay, so you find this, and you plug this back into there, and you also solve for half mr squared. Okay, and then you can find this. And then your work, the answer is just in the textbook. It's equal to this. Okay? 2.9 kilojoules. All right, cheers.